So only depends on what kind it is, not how. It doesn't depend on what kind, only how many. Okay. The first colligative property is vapor pressure. And if somebody asked you what vapor pressure was, just from the name, what would your guess be? Pressure caused by vapor, which is a pretty good guess. So when you take a bottle of liquid and you seal it, those molecules are escaping. But eventually, they'll start condensing back into liquid, and you'll end up with some vapor on top of your liquid. The pressure caused by those vapor molecules is the vapor pressure. So the more molecules escape, the higher the vapor pressure. The fewer molecules escape, the lower the vapor pressure. So it's about how well they're being attracted into the liquid. So in a glass of water, the water has to overcome escaping water. But if I pour some salt into that water, now it has to overcome not just water, but it's got to overcome the attraction for the salt ions, the sodium ions and the chloride ions. And it's got to be more attracted to them than it is to other water molecules. Otherwise, it would have never picked up those salt pieces. So the water's hanging on better to the salt than it hung on to other water molecules. Which means if the solvent is hanging on to solute, it can't evaporate. So the ones that are dissolved, that are hanging on to those dissolved particles, can't evaporate very easily because they're hanging on to something they hang on better to than water. So those molecules don't escape. And this lowers the vapor pressure. So if I put a glass of regular tap water and a glass of salt water with the same levels and set them down here on the counter, we went away for the weekend. When we came back, the regular water would be much lower, and the salt water would be lower, but not as much, because it's harder for it to escape the salt water. But if you remember, the pressure caused by the vapor was what was responsible for things boiling. To make that bubble inside, to make it boil, that's caused by the pressure of the vapor. Okay, so the pressure of the vapor, so if I heat up a liquid, its vapor pressure is going to keep going up because they're moving faster and faster and more escape. Eventually, I heat it up enough, the vapor pressure equals the external pressure, and then it can start making bubbles because it can push the water out of the way because the air can't hold it in anymore. If it's pushing harder than the air, you get bubbles. So because the vapor pressure goes down, it's going to be harder to form bubbles. So the boiling point is going to go up, boiling point elevation. Because the vapor pressure goes down, the boiling point's got to go up. That's not why they tell you to do it. They just tell you to do that because that's the only way to get salt into the noodles. So that's how you taste. That's how you get flavor into your noodles. Okay. Because you'll find it doesn't make a huge difference. Okay. That salt you put in probably raises the boiling point by maybe 1/1000 of a degree because you don't put that much salt in. Okay. So lower vapor pressure, higher boiling point. Salt water boils above 100 degrees Celsius. Not much above, but above. And because these don't depend on what kind of thing you dissolved, that means that the change in the boiling point is determined by the solvent and how much you have dissolved. Not the solute, different solvents are affected different amounts, because different solvents hang on to different degrees. So when we go to calculate how much, we're going to have to talk about how much we dissolved, right? And we're going to have to talk about what the solvent is, because different solvents are affected different amounts. Okay? This is why you pour coolant in your car radiator. If your radiator somehow got a hole and they drained it, and you want to go fill it back up, you go to the auto supply store and you buy coolant. But if you just pour that coolant in, it won't work very well, because that coolant has a boiling point. Well, water boils at 100 degrees Celsius. The coolant boils at about 150. Okay? A little bit higher. But if you mix water with the coolant, the mixture boils at like 220. Because it's harder for the coolant to get away from the water than it is for the coolant to get away from itself. Does that make sense? So that's what you're putting in there, so because you don't want the water to boil in your radiator, because then there's no water in your radiator and you can't cool your engine, and your engine melts into one big metal lump. And that's what happens when you run out of water. Your engine stops because the pistons have melted to the engine block. Okay? Now, freezing point depression is what happens when it gets cold outside. No, that's seasonal affective disorder. Sad. Freezing point depression is the freezing point is going down. Okay? You have to get it colder to make a solid. All right. I don't know how long it's going to take, so you might as well take your stuff, just in case. Okay. So solids got to make a regular repeating three-dimensional pattern, right? The solute molecule is going to make it hard to make that pattern. So in order to make that pattern, they have to be moving even slower, which means the freezing point is lower. Okay. So if that makes the freezing point lower, that means salt water is going to freeze below 0 degrees Celsius. And if it freezes below 0 degrees Celsius, that means it's going to melt below 0 degrees Celsius. Okay? So that you're going to cool it to, you're going to raise it up. Everybody and his brother. It's messy, but it's signed. Your pen is yours. Okay. All right. So to show you that, we've got, oops, where is it? Drag for me. Got Logger Pro hooked up to a couple of thermometers. Okay. So I got 2 thermometers, and I got a container of ice. Add a little bit of water to it. We'll put one of those thermometers into the ice water. We should be able to tell which one it is right away. And the other one, I'm going to put into a test tube. I'll put some water in a test tube. And put the thermometer in there. And I'm going to put the test tube into the ice water. Okay. So we can see that temperature 2 is definitely the one in the ice water, right? Everybody see how I can tell that? Okay. And then if I just let that temperature 2 go until it I just let that temperature 2 go. Okay, so you saw the arrow switch, right? I dragged. It didn't do anything. Okay. So I could keep stirring until it got down to 0. And eventually the water inside the test tube would get down to 0 too, as it melts, right? But I'm going to take and add salt to the ice mixture. So that's outside the test tube. The temperature is now below 0. The temperature is now below 0 because that salt makes the ice melt. If it freezes at a lower temperature, it's also got to melt at a lower temperature. Has anybody ever done anything where you put ice and salt together? What was it? Make ice cream. Because you can make ice cream because you need the ice outside to be colder than 0 degrees. Because I have never put an ice cube into my drink and had it freeze the drink, right? So I've got to get it colder than 0 degrees. So to make that homemade ice cream, you put the salt in and keep stirring. And it adds some, you add some, and it starts melting, so you start having to pour the water out and add more salt. Okay? That's because the concentration of my solution is changing. Right? Continuously, because as the ice melts. So I pour the extra ice out and add some more salt. So that when Fahrenheit made his scale, what he picked 0 was the lowest temperature you get ice salt water. That's what he picked for 0. That's what 0 degrees Fahrenheit is. Okay? So we'll let that sit for a while. We'll come back to it later. Okay. Again, I'm working with water. Different solvents are affected different amounts because they have to make a different crystal. So the crystal they make affects how much they're going to be affected by putting a solute in there. How much does it mess up my crystal formation? How much slower does it have to be going in order to make a crystal? Okay, so the amount of salt I put in affects it, and what solvent I have affects it. So I need to measure how much salt that was. So we are going to have a new unit of concentration. I know it looks familiar. It looks just like molarity, but it's not. It's molality. I changed one letter, it's a completely different unit of concentration. Have you noticed that we've used up all our M's? Okay. In your book, the M for molality will be italicized. Italicized M, lowercase, for molality. And it starts off looking like molarity. It's got moles of solute on top. But the bottom is different in 2 ways. It was liters of solution for moles, right? So instead of liters, it's kilograms. And instead of solution, this is the only one, it's only solvent. That I measure them separately and put them together. Every other unit of concentration we've had, the bottom has been the total. Molality is different. It's not the total, it's what the solvent is, because only the solvent is freezing. Only the solvent is boiling. Okay? But the math with this isn't going to be that hard, right? We could do this math just like molarity, except I need kilograms instead of liters. So try a couple. What's the molality solution with 9.3 moles of sodium chloride in 450 grams of water? Okay, so molality is moles for kilograms. It's going to be moles of sodium chloride. I know the moles of chloride, sodium chloride, 9.3 moles. They didn't give me kilograms, they gave me grams, but I know to change that I just need to move the decimal point 1, 2, 3 to the left. So that's going to be 0.45 kilograms. Or you could get rid of grams, get rid of grams and change it to kilograms. Divide by 1,000. So 9.3 divided by 0.45 is, with 2 sig figs, 21 molal. Extra super hard? Okay. So how many grams of salt are there in 250 grams of a 1.87 molal solution? And by salt, we're talking common table salt, NaCl. Well, I know molality equals moles of NaCl over kilograms of solvent. And I know 2 of those numbers. I know the molality, and I can get the kilograms. So to get moles, I need to do molality times kilograms, right? Multiply both sides by the kilograms. So 1.87 molal times 0.250 kilograms is 0.13. Oh, what units? Well, remember, molal is moles over kilograms. So I'm going to get moles. That's moles of NaCl. But they didn't ask me for moles, they asked me for grams. One mole is 58.44 grams. So I get 7.8 grams of salt. I took 1.87 times 0.25. Did my calculation? 0.13 doesn't make any sense. 1.8, because 1/4 of that's got to be almost 40, right? Yeah, 0.47. Sorry about that. I have no idea what happened. And 0.47 times 58.44. Is 27 grams. Okay. But here's the problem. I'm going to say it's 1.87 molal NaCl, But in my solution, there's no NaCl. Because when I throw NaCl into water, it falls apart into Na plus and Cl minus, right? So I gotta worry about electrolytes are going to have a bigger impact than non-electrolytes. Because if I throw in a mole of sugar, I get a mole of pieces. If I throw in a mole of salt, I get 2 moles of pieces. I put a mole of K2S in, I get 3 moles of pieces. So like I say, NaCl is going to make 2 pieces. It's going to make an Na plus and a Cl minus. So we talked about those 3 colligative properties depending on how many pieces there are, so electrolytes are going to have a bigger impact because they make more pieces. Talked about being molality, so we're going to have to be able to calculate the molality, and then we've got to take into account something about the substance itself. But just make sure, how many pieces will AF3 fall apart into when you dissolve it? So make an Al3 plus and F minuses, and I'd have to make 3 F minuses, so that's a total of 4 pieces. So 1 molar AlF3 would be 4 molar in ions. How about NaNO3? How many pieces is NaNO3 going to fall apart into? Well, remember the secret to this was using the name. NaCl is sodium chloride, 1 sodium, 1 chloride, 2 pieces. AlF3 is aluminum fluoride, 1 aluminum, 3 fluorides, 4 pieces. Sodium, NaNO3 is sodium nitrate, 1 sodium and 1 nitrate. It's only 2 pieces. Polyatomic ions stay together. Because that's what polyatomic ions are, groups of atoms that stay together. So how many pieces in this? Well, if you named it, you would name it calcium phosphate. And there are 2 calciums and 3 phosphates, so that would be 5 pieces. Are we okay with that? How is this doing? Huh. Let's get it colder. So, why molality? Because the size and the change of the boiling point is determined by the molality. The more concentrated the solution, the higher the boiling point is going to be. The reason why we need molality is because molarity and percent solutions don't work for this. That's why we need it. Because here's the equation. Delta TB, that's a T sub B, B for boiling. So that is delta TB is the change in the boiling point, the change in the temperature it boils at. Delta always means change in, so delta T means change in temperature. And since B is boiling, the change in the temperature it boils at is equal to KB. KB is called the boiling point elevation constant. And it's a number you look up on page 495. And what you look up is the solvent. We said the different solvents were affected different amounts. KB is where you see the effect on different solvents. That makes sense? So we said one of the things was what solvent it is. KB is about what solvent it is. That M, anybody guess what the M is for? Molality. And when you look at your book will not have N at the end of it. I put it there because the book tells you have to do N, but they don't actually put it in the equation. Because N is the number of pieces it falls apart into. So we just saw ionic compounds. We could figure out how many pieces they fall apart into. Sodium chloride fell apart into 2. Aluminum fluoride fell apart into 4. Calcium phosphate fell apart into 5. So those are going to be an integer number. What if it's not ionic? Sugar, C11, H22, O11. How many pieces is that going to make when it dissolves in water? 1. It doesn't fall apart, so you get one molecule at a time. So for molecular compounds, N is 1. I put in 1 mole of stuff, I get 1 mole of ions. I put in 1 mole of sugar, or not ions, but dissolved pieces. I put in 1 mole of sugar, there'll be 1 mole of sugar dissolved in my stuff. I put in 1 mole of salt, I'll have 2 moles of stuff, sodium and chloride. So see how this equation just has the 3 pieces that we talked about affecting how much the boiling point was going to change. Well, that's how you do boiling. What about freezing? Well, the size and the change of the freezing point is determined by the molality. And the equation's going to look a lot like the one we just saw, except instead of T's, or instead of B's, it's going to have F's. So instead of delta TB, it's delta TF. Delta TF, the change in the freezing point, equals. Now here's something different. This one's got a negative sign there. Why a negative sign? Well, because the freezing point is going to go down. That's a negative change. KB was positive because the boiling point is going to go up. So we talked about the coolant, making it so your car won't boil over. In Michigan, they sell the same jug and call it antifreeze because it raises the boiling point, but it lowers the freezing point. Same material. So when you dissolve stuff, you get liquids for a longer range. Okay? So it's negative because the freezing point is going to go down. Kf is a different constant. Make sure you look up the right table. Kf's are on page 494, not page 495. So if you're talking about freezing, use the one that says freezing point constant. If you're talking about the one that's boiling, say boiling point elevation constant. Of course, M is molality, and N is the number of pieces it falls into. So the equation, the difference between melting and freezing is it's going to change a different direction, and you're going to look up a different K. That make sense? Notice this gives us a way, by measuring the freezing point, we can find molality, which means if I know how many kilograms of solvent, I know how many moles. This is another way of finding molar mass. You put in 10 grams of stuff, see how much it changes the freezing point. That'll tell you how many moles you had, and you know you had 10 grams, so you know how many grams for that many moles. So another way they can find the molar mass of an unknown is how much it changes the freezing point. Okay. So let me tell you about my problems. What is the boiling point of a solution made by dissolving 1.2 moles of NaCl in 750 grams of water? Now we know the equation I want to use is delta TF equals negative KF times M times N. So I'm trying to find the, oh, I'd actually, no, that's freezing. I want boiling, don't I? Give it to the negative, make them B's. Okay, so the first thing I do is I go look up KB on page 495. And it says KB for water, because it's a water solution, is 0.512 degrees Celsius per molal. Now I need the molality. Well, molality is moles of solute over kilograms of solvent. So I had 1.20 moles in 0.75 kilograms. And 1.2 divided by 0.75, the molality is 1.6 molal. So I've got to figure out the molality so I can do that. Times the number of pieces. How many pieces is NaCl going to fall apart into? Times 2. Okay, so 0.512 times 1.6 times 2 equals 0.512 is 3 sig figs, 1.6 is 2. That 2 is a counted number, so it's unlimited. So I should have 2 sig figs, 1.6, and my units work out to be degrees Celsius. And you circle that answer, and Mr. Green marks it wrong, because you just said water was going to boil at 1.6 degrees Celsius. We didn't figure out the temperature it boiled at. We figured out how much the temperature it was going to boil at changed. What temperature does water normally boil at? 100 degrees, right? So to find the final temperature, I have to add the 100 degrees, and I get 101.6 degrees Celsius. And that goes back to the question about, do you put the salt in your spaghetti water so it raises the boiling point? 1.2 moles is 70 grams of salt. Do you put 70 grams of salt into less than a quart of water when you're making spaghetti? No. So you're not doing it for the temperature change. Because even if you did, you'd only get a 1.6 degree temperature change. Okay? So it's not about the temperature change. It's about flavoring the noodles. Okay, so what about the freezing point? What's the freezing point going to be for this same solution? Well, delta TF equals negative KF times M times N. I go look up KF on page 494. And I look it up and it says 1.86 degrees Celsius per molal. negative 1.866. Notice the K is bigger, so freezing point is affected more. Times molality, it's still 1.6 molal. That hasn't changed. And the number of pieces it falls apart into is still 2. So 1.86 times 1.6 times 2 is, with 2 sig figs, 6.0, negative 6.0 degrees Celsius. And if you circle that answer, I'll give you credit, but you should actually do some more math. What temperature does ice normally form at? 0. So if I add 0 to that, that's going to be my temperature. Now, if it's not water, that's not going to be 0. They'll tell you what the melting point is. Make sense? Okay. Now, okay, so that's what you can do on the homework. Now, let's see if this worked. Okay. This has been sitting there for a long time, and it's cold. The question is it cold enough? Okay, if I do this right, and it's actually down below 0, I didn't get it cold enough. I'll try it again tomorrow. I'm just going to try to super cool the ice, but I never got it down below 0. We'll try that again tomorrow. Quiz tomorrow.